Welcome everybody. We're not going to waste your time today, I promise. 1:01 p.m. Welcome to our second week of summer 2020. Summer 2024. Middle school teacher professional development. We are doing this virtually this year, and we're so happy that you could be here to join us. Today, we are going to be talking about wavelengths in general, and we have several lessons that we will be going through. I guess it's not just wavelengths. I shouldn't have just said wavelengths. We're going to be talking about waves today, but some new lessons about waves. One of those involves wavelength, and there I think I've successfully opened this up now. So with that, I'm going to turn it over to Stephen.
All right, we'll do a quick share screen. First thing we're going to talk about is we have two that we've never shown in middle school stuff, but then this one is something that we revamped from an older, right?
Correct.
Right.
Mhm.
And it was a kind of an investigation of our systems. I mean, yeah, I'm reading the screen to you, but I thought you'd be proud that I could read big words. But investigation.
Yeah.
All right, and so this one we started off with just a little video. That little video is it's simply we took a car to the top of the parking garage. Oh, I missed that car. It's the one that I correct. But like bringing back emotional times. I'm sorry. But and we're recording from up there. Can you guys hear us all right? I know you can.
No, I can see.
Oh, okay.
Thank you.
It's okay.
Yeah.
I see. I know you can. But you're 6 feet. But all right, we have multiple confirmations for yes. Yeah. Okay, great. So we started off with this one, just like with an engagement piece, something to get them thinking, going. And that's a shorter video, not very long. We took the car to the top of the parking garage, put a veneer thermometer in it, and we recorded what happened, which naturally it heats up in the sun. And so we're not going to do that here next week here in the Midwest when it's going to hit almost 100. But so we kind of wanted to just kind of give us something to think about and give us a reason for investigation. And the reason is we're trying to figure out the whole car thing, why it's warming up. And then I like giving them a fun quest. And so we used a picture of Leo, one of my puppies. And we talk about he likes to go with us, but in the summer he can't because it's too hot setting out the sun when we're in the store. And so why does the car get hot sitting in the sun? And why does the car get hotter in the summer than winter is the second question. And then we explore that much later. But what we do, what I like doing for years is we'll do a web. Usually we do these on the board. You have all kinds of graphic organizers. I mean, you can do it electronically, but we've just done these usually on the board and have students come up and just make a web. I know if we click on this, it'll just blow up what the group I asked. The first group I asked, I just recorded what they put down, and that works for us. And so your kids will say similar things, I'm sure. And so, all right, so to understand that, we probably need to first talk about waves, start understanding what waves are to get us down this quest of understanding where the car warms up. And so with this page, we have parts of the wave. So we have the waveform there. We have the terminology vocabulary, your crest, trough, and all those different great things that we love teaching. My favorite is talking about wavelengths because that's where we usually use a little slinky thing. Now we've done this demo for several videos for professional development. 2020, that was 2021's, 2021's. But all that is, we're not going to do a big video on it or anything. All that is we have these coiled springs. I like the plastic ones best, by the way. Go ahead and love it. And it's nice. You can just do. Can you see that?
I can now.
Yep. All right, slow down a little bit more. You can do that where it has the nice slow wave. Then if you speed up and go really fast, you can get more nodes in there. And so, yeah, it is hard to see at that. But I like these really long ones because you can, I walk through the class and do it. And so I'll string it out. I'll give a student this and I go away and tell them to go back. So I like these. The metal ones hurt just a little bit when the kid releases them because they let go by accident. And we'll just assume it was next anyhow. And so, and these are harder to tangle up. It is doable. I've had students tangle them up, but it's harder to tangle these up. And so I do like them quite a bit better, the plastic ones than the metal. And these don't, the metal ones get bent out too easily here. And then when we're talking about waves, of course, as a transverse, when we go talk about wave types, we can also do our longitudinal waves with this, which helps when you go into, we do it now. Well, that's really fast, this short. You see it a little bit better if we stretch it out a little bit more, but that's that.
So oscillating it on a table.
Well, yeah, it's what I was gonna try to figure out how to do. Yeah. I can go here. But, and then I've had some teachers that are a lot more safety conscious than I am. And, they're afraid of going to the classroom. So you can do this on the floor and they can be able to see. You can do it on the floor, on a long tabletop counter, whatever. And so it'll be obvious. See, we're going nice and slowly there. Then we speed up. So there's that. All right.
Okay.
And so now we'll go back to share. That's, I'm like, why isn't this on us? But it's the one Bill has in here. But we'll go back to there. And so there's that one. And then we already started mentioning types of waves. Of course, we start with mechanical waves because they're boring.
Boring.
They're not. But and that's where we get our transverse. But we talk about these with our earthquakes. So when we do our earthquake units, it's nice for them to have that knowledge, that background knowledge. So I like doing a little bit with waves prior to that. But and so and of course we've just showed both these. Showed it. I think it's shown. Show. We all. Oh. Big thing about mechanical waves is I'm sure you guys already know is they do require a medium to travel through. And since you can hear me, we know there is a medium, actually multiple at this point, the air to the mic, anyway. So it's, but sound waves, water waves, blah, blah, blah. And then, you want to explain this?
Yeah. So then what we did is we've gone through our demo repository, which we'll pull that up towards the end. We'll show you how to get there, but we have a repository. It's searchable by keyword. It's searchable by title. You basically type anything into a number of fields and find a demo that you might be looking for during your normal classroom teaching. What we went through is we typed in wave and we looked for all the demos that we have that we've entered a keyword wave in. And so these are all demos, or in some cases, they're a longer video. We'll have both in the demo repository, either a YouTube short, or we'll have a longer video where we explain to the teacher how to set those up. But all of these are modeling a type of mechanical wave. So the wave machine would be Bill and I using the wave machine that we built. We're kind of watching that through. So I don't know if we want to go through and try to
You want to see one?
Do it. Yeah, do a couple.
yeah.
Here, I'll click it. Make sure you hit the back button. But yeah, with this one called the wave machine, something we put together just with skewers and duct tape and those little balls.
Mm-hmm.
We put on the end, and it's just demonstrating.
We like this one because you're really showing it's the energy being transferred. It's not, you know, each of those skewers with the wooden balls there, they're not moving. They are moving back and forth, but they're not changing position. And so really what we're seeing is we're seeing the energy moving through those. It's just a nice visualization so that waves are that transfer of energy. You're not actually changing position.
Yeah, I think it's a really great demo for that.
Yeah.
But there's some, and then of course it's of course the bowl where Austin uses the Tibetan bowl. It makes all those noises and stuff.
Yeah, and we do have sound. We might not be hearing the sound just because of the.
Yeah, I have no idea if they're even.
Yeah.
I don't know what this is.
To vibrate. It makes that noise, and you can actually see those vibrations. You can see those waves on the surface of the water. When the vibrations get big enough, it even sends up like a shower of drops. Because the water's vibrating.
So Austin does a really good job explaining what's going on with these. Third one, we have both the longer version, shorter. Sounds of silence. That's
Alarm clock in a vacuum.
is that
Yeah.
one or this?
Well,
Oh, is that the long,
that's the
short
long
one?
version and the short version.
Dude, you can check these out. They're fun. Fire by reflected heat. That's lighting a match from a distance. Using a whatever you call it. String phone is.
The string phone clip's kind of cool. It's very short, but what's nice about that one is it's showing how you need that medium for the wave to travel through. So in the first part of that, it's just a cup phone. So there's a string and it's holding two styrofoam cups together. But in the first part of the video, the string is kind of slack, and so you can't hear it as well. But then when the kids pull the string kind of tight like that, then you can hear it much better. We have a little microphone clip to the cup nearest to us, and you can hear that better coming through that.
So those are some demos to help students understand.
Yep.
We love using demonstrations with things. It kind of helps. Then we go into electromagnetic waves, which do not need a medium to travel, and they can move through space, through the vacuum of space. And this is obviously the sun, everything with the sun. And this here is still not doing it.
The graphic there does.
Oh, okay. Hit down here. Okay. It just gets that bigger. That's a NASA graphic. That it's just it's the one I like best, so it's the one I always use. And Sarah lets me have my way because it's not worth fighting if she has another one.
No, I like that's a good one. That's a good one.
Oh, you agree with me?
Yes.
Didn't expect that.
Oh. Okay.
But and then here we break down. Here's where a lot of changes. The most changes have happened in some of these, from longest to shortest, which we can see here what they were. We talk about the different ones, and we have different demos and things. Part of them radio waves. Of course, we talk about what that is. I mean, a lot of people don't realize we talk about radio waves. Your cell phone is actually on radio waves still. It's not just the AM, FM radio that used to be in cars. But actually, I think we still have one. I don't know. I just use my Bluetooth.
Yeah, I think we still have AM, FM.
Exist?
Yeah. Oh, yeah.
I just use Bluetooth. You old people don't use social media. You still use the AM dial?
Oh yeah, that's it. Yeah.
AM?
Yeah. You know what? There are a couple of sports broadcasts that'll come through. You can get them pretty clearly through AM stations.
I'm kind of embarrassed to know you right now.
I'm okay.
Okay.
That's fine.
Then microwaves. Yeah, just throw popcorn in the microwave or something.
We got to do better than that.
Well, that's all I got.
Yeah, I know. Right now, that's what we
I
have.
don't have time to put together. We do have a professor we're working with, if I remember right. It does a lot with it. We will have stuff for that later. But then the infrared cameras do a really good job. And that's where you can see the heat pipes, and then you can see the person standing by the elevator. And it's kind of really cool. You can pick up all of that in infrared. And something else is the remote control. A lot of remote controls use infrared. It's so your phones, now if you have an iPhone, they have a filter on it that blocks infrared.
Because they're better.
Because they're lame, like Bill. But most of your Android phones don't have that. And it's just like, you get a really cheap point and shoot camera.
Yeah.
Sometimes they have a filter over it. But if you get a really good camera, it won't. Take that, Bill.
Have to tension.
Get 8 mil from.
Bill's taking advantage of his post behind the camera. Right.
Someone tell Bill to make a post them. But then, of course, your IR thermometer. Infrared thermometers are very handy. We use those all the time with stuff. Infrared cameras to know. Then we can pull up remote sensors.
And I just want to clarify a little bit, just in case you're like, wait, what were you just talking about? If we were just looking at a TV remote like what's in this picture right here, we would not see with our own eyes that infrared glow. This was taken with a camera that does not have that infrared filter or anything on it, which is why we're able to capture that photo there. So again, if you're pressing a remote control, you would never see that light flashing at the front of it with your own eyes.
Correct.
Yeah.
Good clarification.
Yes, Bill.
What? Thank you for calling on me.
Yeah.
So everything you're showing on this website right now, is this background information with some demo stuff in it? What?
More so, yeah.
Okay.
This is, I mean, I would show the demos and stuff to the students, but I wouldn't show the students this page.
No, this is just background information
Yeah.
for the teachers and stuff
Yeah.
like that. Okay.
Correct. Yes.
I kind of wanted to clarify that out.
Yeah.
Then visible light, we're gonna come back to visible light next, because we have an entire lab that has a virtual option that Sarah had put together, for visible light. And so I think that should be entertaining. And, of course, if you have access to like a visual spectrometer, you can use that. Prism glasses, you can use your prism glasses, which you probably can't see. Take that, Bill. You see the rainbow effect on that?
Little.
I can't see what they can see. Oh, wait, if I stop sharing, maybe they can't.
Hang on. Hang on.
Get a little kind of a glimpse of it. We would need to probably, oh, okay.
Right?
That's better.
You kind of get the idea. So it's a much more dramatic effect, obviously with the lights out. And if you have a source of some kind. So what we're seeing in the picture here is exactly what Bill was just doing. We placed one of these prism glasses over a camera lens, but we had lit a candle and we had that flame. And so we're observing that flame. It's very dramatic for students when you kind of do like a countdown, a 3, 2, 1, and then you strike the match and light the candle in a darkened classroom. And they really get a sense for that continuous spectrum that we're able to view, that visible light. Of course, they're probably familiar by the time they get to middle school with the Roy G. Biv acronym. And one of the things I always like to point out, especially with middle school students, to get them thinking about the concept of wavelength, is that that the red, just past infrared, we have the red visible light that we can see is the longest wavelength, and the violet is the shortest wavelength. And when they're looking through the prism glasses, like what you can see here in this picture, the violet is always the closest color that we can see to the light source. And that red is always the farthest from the light source. And I kind of challenge them, can you move your head? Is there a way that you can position your glasses to ever change that order? And give them a couple of minutes to try that, to test it out. And the answer is no. Violet's always going to be closest because it has the shortest wavelength. They can't go as far. So you always have the shortest wavelengths, and they're in that order on purpose because you always see that Roy G. Biv, you always see that order in a rainbow because of the wavelength. So the longer that they get, the farther away from the light source they are. And so red is always the farthest because it has the longest wavelength, and that's where we detect it is the farthest from that light source when we're using the prism glasses. Okay.
Yeah. And then UV, we talk a lot about UV, obviously, in this time of year.
Yeah, especially
When it's getting warm, and talk about that. Of course, you can use UV beads, black lights. Is this where we're gonna show those?
yeah, we do.
This is where,
Do you want to talk about your index?
explain the index first. The index you can put, 47907 is where we are.
Mhm.
When you hit that, and it's going to pull up the EPA website and let us know right now Lafayette is 9, which is very high.
Okay.
And so with the 9, we, protection against sun damage is needed. If you're going outside between noon and 4, take steps to reduce sun exposure. A hat, sunscreen are a must, and make sure you're seeking shade. And so they tell you, and then it goes further into it a little bit here. But this is good. That way you can put in exactly where you are. So we're here in Lafayette area. And so you know that, yeah, it's high here.
I love that it's real-time data that they can get from this and that it's also based on location. And I think that could make for some really neat research opportunities or investigation opportunities throughout the school year even. So maybe when you first start the school year, whether it's August, September, whatever that beginning of the school year looks like, you might look at some UV data there, and then maybe again in a couple of months. So when you have a season change, how do the UV values, which day to day they'll change a little, but do we see any changes with the different seasons?
We can go hourly.
Oh, that's
We
cool.
want. And so here's the forecast. Remember, this one's a forecast.
Okay.
So,
Yeah, it's such a neat tool from the EPA there.
all right. So that's that. And the UV beads, you can get at any of the science supply
Right.
things. Just stop that again. You get those from any of the science supply catalogs are the UV beads.
Yeah.
So I used these in teaching elementary,
Mhm.
and we even we would make like bracelets. Then we before we go out recess, then we go out for recess, and then when they're out there at recess, they would get to see the beads change colors.
This is a really neat, we just taught this in a middle school classroom this spring. We were talking about observations and inferences, and we had the students observe these UV beads before they knew what they were. And then we showed exposing it. Stephen's got a little handheld UV light here. If you have a plug-in black light, you can use something like that. And even if you need to just get close to a classroom window or take a quick trip outside and see that, the students are amazed if they've never seen the UV beads before, how quickly that changes. They want to know why it's changing. It's very exciting. Then they want to know, will they go back? And so this is a really good opportunity for observations and then making some inferences from those observations. Why do the UV beads change color? Do we know?
Well, you do.
Yeah.
You just did a whole thing on them.
Yep. So there are some, basically for a middle school level, there are some specific molecules mixed into the resin that makes those UV. And when they receive a specific kind of energy, so energy from ultraviolet light, whether it's a black light or the sun or anything, it changes the shape of that molecule, which then induces the color that they see. And then once that energy kind of dissipates, once it kind of goes away, then that molecule just kind of shapes back into its original form before it was showing that color. And so then it goes back to that clear color, that white color for the bead.
Nice.
Yeah.
All right. That is for remote sensing.
Okay.
Then the x-rays,
love
we
this
do have you love that one?
Yeah, I do.
Can they see, could you guys see the short? Last time I showed the video, could you see it all right on your screen?
It showed up.
Why don't you try muting?
Try a minute. Well, when he did this with this.
There's a surface X-rays are invisible, we can't see them, so that the closest we get to seeing them is when the screen fluoresces. Here, look at the front and hold it right. So surface X-rays are invisible, we can't see them, so that the closest we get to seeing them is when the screen fluoresces.
That's literally like, it's just a really short one.
Did you try your?
Hold on.
All right, is your volume?
My volume, I never changed.
Oh, you
never
never
changed.
changed it. Oh,
No.
okay.
Because I could hear whatever you guys were doing. I could see it moving up and down.
Oh, okay. You can still see. Okay,
Yeah.
got it. Yeah. So, like our guest, in that short, her name's Leanne. She mentioned she's an X-ray technician. Yep, over in the Purdue School of Veterinary Science. But yeah, we can't see X-rays either. Just like we can't see infrared light, we can't see ultraviolet light. We certainly can't see X-ray light. But when that screen, there is that fluoresce very quickly. And like Leanne was saying, that's the closest we can get to our eyesight detecting any X-rays, even though we're not actually detecting those X-rays.
And then down on gamma, if you want to go to gamma, we do have, and this is explained in last week's
Yes.
Session that we did last week. I know not all of you could attend that. We started them earlier this year, and we agree it was not the best choice, but we were trying something different. But we do have radioactivity. You want to explain that?
Oh, first we do have the link, and again, we'll show this at the end of our presentation, how to get there. But we do have a link to last week's professional development session that we did over all things geologic timescale, but then introduction to radioactivity, and then what is a half-life. And so all these are middle school appropriate instructional lessons, or instructions and lessons for teaching about these topics. And this introduction to radioactivity, within this, we have a virtual looking at the effects of distance and shielding and how that affects their exposure to radiation. And this is just an entire lab that students can do right here on the page. There's the worksheets and things that they would need. But we go through with some different sources. One of those sources happens to be a gamma source. We also go through with an alpha source and a beta source. And we're using this nuclear scalar. It's a Geiger-Muller tube inside of a kind of this apparatus, and it detects detects radiation. And we have, just like we said, some different scenarios where we've taken some measurements based on either distance from the sensor or shielding materials that might be interfering between the sensor and the radioactive source that we're using.
So, and yes, that was gamma source on shelf 2.
Without any shielding. This is part of this is the shielding portion of that lab.
That's what I was saying. Just interrupt me.
Um,
We talk about this?
We probably did. I have short attention spans.
And so this is the first one. It's just the gamma source setting there, nothing between it. Then we go up here if we want to see the gamma source one, and then further and further away how it does. And then, or we can see what different materials, how it shields gamma radiation. Or alpha and beta too. We have a whole virtual lab set up for that. Getting back to here. And then of course key characteristics there they're always transverse waves. They I don't know why we included that, but whatever. They don't require a medium, they travel through vacuum. But now that we understand waves, we went into seasons, start understanding the seasons, because that was part of our thing. And this one is a short video, again, that has a nice setup. I do this setup in the classroom when I'm teaching this tilt of the earth and talking about direct and indirect. What this is it has 5 radiometers set up, and 3 of them, the 2 ends in the middle, have a thermometer beside them. And the floodlight off to the side that when you see when it first starts, then we zoom in, is pointing directly at the center one. Now it's closer. There is one there. These are the far right side here is closer. Awesome. And so we can see how the middle one is heating up more than the closest one. And of course, the farthest one away is also getting indirect light, but it's furthest away, so it's a little cool. And this is a great demo to do in person. And even if you have one, you can move the light further away or direct and change the light. I actually do this. I start off using flashlights and I don't tell them what they are. I have a set of these. I put one at each lab station. They're not allowed to touch them, but they have to try to figure out what they are and what they do. And so it's a fun little investigation. And we have that lesson plan link there too. Maybe. Maybe not.
We will have that lesson plan there. We have it.
This is awkward.
Yeah.
But we're good.
Yeah.
Must be set the wrong setting on it. But we'll fix that.
Mhm.
We'll make a note, fix that. Then there's this graphic talking about direct light versus indirect. We'll talk about our seasons. Then the other videos that we put down here are why some planets have seasons and why we have seasons. And that's a shorter version that a student did. And I think that's long as students too.
And that's part of our
Grad
kids'
students.
Yeah.
Okay.
Mhm.
Which we'll explain that if we're done, if you haven't seen the kids' STEM degree stuff. But then this one's part of the STEM degree, the albedo. Also, the Bill, Sarah, and I put together for that is literally just showing that the darker cloth, white cloth, and the infrared. And then a fun one. Let's go ahead and that we do is with a laser and a white balloon.
We're waiting to see
what happens?
Can we get the laser to pop the blue?
No, you had to tell them. I said, we're going to see what happens. And you're like,
Exactly.
oh, no, you get the way the answer all the time. That's what you do.
It said in the title, will the
They
laser
didn't
pop the
read
blue?
that. Oh my
Well, I read it.
Oh. Oh. 42 seconds in. It took you what? 5 seconds to give away? Do you read the last page first?
Yes. I don't like surprises.
You probably really do.
No, I do.
Oh,
I definitely do.
that is,
I
I
know.
don't think we can be friends.
Oh,
Whoa,
that was fast.
Yeah, it happens quite quickly. How do I get it out? Oh, we're there. And so that's a fun one to show. And then we go to Google Earth, look at dark versus light on the Earth to talk about what could happen, and which brings us to our convection currents. And the convection currents is a video we put together, 4 minutes long. We won't do the whole thing. We'll just show you. We filled up a container with hot water, another container with ice, and then we put a tub on top of them, dropped in food coloring, the red over the hot, of course, just for the visualization, and blue over the cold. Then we watched what happened. And so, very pretty. You can watch and see what happens. We'll fast forward here. You see the red goes up and the cold just kind of moves. It starts a current through there. And that is a really easy way of doing that one, by the way. For years, we would always do it much worse. If you've not done density straws activity, if you want to do something with density, it ties in with convection current. So we put it on this page. I realize it's kind of a separate thing. And I have some of the teachers I've worked with for years will do the density straws activity. Their first lab every year, they'll do the density straws. Because really it's the way I teach it. It's all about not saying it in a lab report. And so it's instructions one. It teaches density very well, but it's more of an instructions.
Exact instructions.
Yeah.
Yeah.
So that's what we have them do. But it does a great job of actually teaching and having them understand density. And greenhouse, finally we get into the greenhouse effect, and we have students that did part of one of our kids' STEM degrees. They did a video on that. Make sense?
Yes.
All right, so we said we would go back to not that page. Not that page. Not that page. Move this.
Yeah.
Light, measuring visible light is what we said we would come back to, and we are there.
Okay, so we had already talked about if we were going to use the prism glasses to look at a continuous spectrum, to look at a rainbow, we would need a source of white light to be able to view that continuous spectrum. So when I say continuous spectrum, I mean rainbow. It's a continuous spectrum because all of the wavelengths of white light are present. There's nothing absent. There's no sections missing. And we know that, or we might not know, but there's actually where you can have continuous spectra. We also have something called line spectra, and that's a little bit later in chemistry. It's not, if you had the resources to show middle school students, it can be kind of fun to get them asking questions and thinking about that. But line spectra are also there if you use a prism glass for a light source that is not coming from white light. And so you can see in that case, you might have certain frequency or certain wavelengths of light that don't show up. And so, what's that?
Bands.
Yeah, bands that are there. But we're focusing on visible light right now. That's what we can see. And we want students to be able to get the idea that the visible light can be measured, that we can measure that visible light, and that the different colors can be associated with certain wavelengths. And so how might we measure visible light? And that's all that this is doing. This is a virtual lab where we use a spectrophotometer, or we did use a spectrophotometer here in the lab, but we realized that not all classrooms have access to a spectrophotometer. So what we were able to do through the magic of video is that we were able to capture the change of wavelength in a spectrophotometer and include that as a video. And we're going to practice with that here in just a couple of minutes. So in this, we're having students, first of all, learn about wavelength and observe how visible light can be measured. But then also what they're going to do at the end is compare their observations of visible light to develop ranges of wavelengths for different phones. I'm so sorry. Having
I can't control someone rolling this
Yeah.
down the hallway.
Yeah.
Are you gonna explain what a spectrophotometer is?
Absolutely,
Okay,
yeah.
all right,
So
all right.
a spectrophotometer is an instrument that we might have in a lab that has a light source in it that is going to emit light at a certain range of wavelengths. And we're able to manipulate the wavelength that it is emitting at any given time. And when it is emitting a certain wavelength, we can either collect absorbance data or transmittance data. Is there something? I think it's just absorbance and transmittance that we can look at, and we can set it to either 100% absorbance or 100% transmittance or anywhere in between, and that we can collect that data and we can do some different things with it. We can measure the light at different wavelengths that is getting absorbed or transmitted. So this has a lot of applications if you're trying to determine like the concentration of a solution or I don't know, there's a lot of applications that we have for this, but in the general sense, we're in this lab, we're using the spectrophotometer as a tool to measure the wavelengths of light that it is able to emit. And it just so happens that the spectrophotometer emits wavelengths mostly in the range of visible light. And I'm going to pause for just a minute.
We have someone rolling a part down the hallway behind us. Sorry.
Okay.
I can't stop that.
Yeah. Now for this, I just wanted to point out, as with all of our virtual labs, or I should say most of our virtual labs, there is an opportunity to request an answer key for this. Most of the things that we're going to be showing, we're actually, the answer key is going to be more just some sample data that we'll share with the teacher that requests this. What we do with this and with all of our virtual labs is we like to collect these metrics so that we know, first of all, who's using the materials. Secondly, we like to try to avoid handing out answers to students. So we like to verify that the person that's requesting the information is an actual classroom teacher. Because believe it or not, students are tricky and they'll try to get on and request answers from us, and we will shoot that.
Busted a number of them.
We really have. It's kind of fun. And anyways, but also we like to know initially, we know we can't do this forever, but we like to know initially how many students are using that in that first time that the teacher might be using the virtual lab. All of this helps us make the case to our departments and to the college that it's valuable to continue developing these types of resources that we're then able to provide for free to educators everywhere when we can know kind of just a rough idea of who's using it, where they're using it, and how many people that we're able to reach with these products. So that's why we're asking for that. We'll also at the end, we'll jump down to our next gen science standards that we're able to address with this. But we can see some vocabulary and the materials. But again, if you don't have a spectrophotometer, don't worry, because we're going to do this virtually right now. So we have linked a one pager to the procedure, but we're going to look at the procedure ahead of time down below. This is just if you wanted to print that out for students. We also have a data table. So we'll open this and show this data table. As they're watching the video that we're going to watch in just a few minutes, they'll be able to record initial and final wavelengths where they're able to observe these colors. And then there are some discussion questions as well. So this is on there as well. You're able to either assign it through a learning management system or print that off. But then this Google Sheet is kind of the important piece of this because this is going to be a group effort of collecting data when we do this. Now, again, if you follow the link above and request a key, I will share sample data that we collected last summer so you can kind of get a sense of what that data looks like. You could even use the sample data that I share with you and continue adding data. So you can use those as kind of your starter points, and this will make more sense once we start using those. But to do this, right now, this link, when we open it up, is going to be a view-only link. And it's on purpose for a view-only link because we want you to go ahead and save this into your own Google Drive. And in case this is a new procedure for you, we just wanted to quickly show you that you can go into, actually, I think if you just click on, oh no, never mind. If we just go into File and then Make a Copy, and as long as you are logged in to Gmail or your Google Drive or something, this should go straight to your drive, or you can organize it in whatever folder you might like. So I'm just going to go ahead and make a copy of this that we're going to use today. And once we have this saved, you're going to notice this field up here, we really don't want to mess with. I kind of have some preset. It's going to average out some of the data that we're using. And as we start adding data, it's going to create this really awesome waterfall chart for us that we're going to be able to use to determine wavelength ranges for each color. So what we're going to do now, and I'm really excited to try this, and I apologize in advance if this doesn't work, but we're going to assign, right now I see that we have 11 attendees. We are going to assign a row to each of our attendees. And so Bill is pulling that up so I can kind of see, but where we want to start adding data is going to be going across a row. So each person is going to get a number, and we'll say that here in just a minute. So be listening for your number. But we are going to drop a link to this Google Sheet into the chat. And then you are going to get assigned a number for a row. And then we're going to play the video that you'll have available. And this is, again, to be used instead of using a spectrophotometer. This is a virtual option. So we'll be able to watch this together and determine where the wavelengths begin changing colors, or yeah, we'll just say that. So right now, we're just going to start at the top, and so listen for your number, and this will be the row where you are going to enter your data, and then
This is really easy. This is really easy. Don't stress about this.
Yeah,
I know if I was sitting there and be like, what? She wants me to do what? Wait,
yeah.
what? This is really easy.
We haven't shared the Google Sheet yet, but we will. So give me just a minute. But here I'm just starting where I see the names listed for our attendees. And also this is optional, so it's going to do it whether you input data or not. But I'm hoping if you're there and if you're listening, I'm hoping that you'll try, because I think it'll make it better if we're all inputting data. But I see Amy Morgan, and we'll give you, you'll be row 24. Chris Bigelow, we'll give you row 25. Emily Justice, we're going to give you row 26. Gina Bobbitt, we're going to give you row 27. Helen D, row 28. I see Herrera, we are going to go row 29. Jamie Black, row 30. Kathleen, row 31. Michelle, row 32. Molly, row 33. And then Shauna Rifle, row 34. So one of those rows, again, you'll just be adding data into your row. And I'm going to go ahead and drop the link to access this spreadsheet into our chat.
This is really kind of cool, by the way.
Yeah, I'm excited. I hope this works. I've kind of been anxious about this today. I am changing this to editor. Anyone with the link is an editor. And there's the link. And then our WebEx is going to be
Under WebEx, where did it go? You have to stop sharing to do that.
Oh, okay. Okay. Okay, so this is going to everyone. Okay, so I just shared the link. So if you could grab that link, and then we'll go back to share.
Yeah.
Amen. I didn't do something wrong again, did I? No.
There we go. Okay. Okay, and I do see people getting on there, and this is great. So now we're going to switch screens, and we're going to go back to the understanding right here. Now, we'll play this video here in a moment. I see a lot of you have found your row, and that's great. We'll see how all this is working here very soon. But what I'll just talk quickly about these next things that we see, and then we'll play the video, and hopefully we'll be able to get some data from that. I will also share the video in the chat as well, so that if you want to take a minute or two and watch the video on your own and enter that data, that might work easier than us trying to play it for everyone. So we'll see how that works. Right here, this is just, they recorded me giving these lab instructions. Last year, we had a group here in person. We were doing this. And so if you wanted to listen to someone instructing that, if you have spectrophotometers and you've never used them before, you might watch this just to kind of see how you go about kind of instructing, getting them ready to start taking measurements with the spectrophotometers. The procedure, you're going to find this is for if you're using the spectrophotometer. So it's a little technical here. It just kind of walks you through to make sure that your instrument's all set up and ready to take the measurements. Yep.
Will all spectrophotometers do this?
This is specific to the Genesis spectrophotometer. And so other
near ones didn't work.
Yeah. Oh, that's correct. Yeah. So what we're getting ready to do, and you'll see this here in a moment, where we actually view the wavelength that's being emitted. Not all spectrophotometers will give you this.
The new ones won't do it.
The new one.
The technology's too high.
Yeah, we were on the phone for a while with Vernier, kind of troubleshooting this, and they weren't able to do this. So that's unfortunate. But again, this is why it's that much more valuable to have a video of this to be able to get the data points. This is an example of what that results chart looks like, but we're going to be directly inputting the data onto the spreadsheet. And so, I see a lot of you already there. That's very exciting. I'm excited to start showing this. So again, here's our virtual option. I'm going to open this video in a moment, but I'm also going to, well, actually, I'll do this now. I'm going to share the video link as well in the chat, so that this is something that you wanted to. Are they able to go to a different browser and still be in WebEx?
Oh yeah.
Yeah,
Oh,
yeah. So if you want to jump to a different browser and stop sharing, I'll throw this as the link to the video. Okay.
And you don't have to open it. We'll play it right on the screen.
We're going to play it here, but this is just if you're like, actually, I want to see it myself.
Obviously, but yeah,
That's fine.
if you're like Sarah, control.
Yeah, I would have to see it myself. So I know I had issues. Okay, here we go. All right, so we're good. Do we just play? And it, undo.
Make it as big as possible.
There we go. 350 nanometers. 351. 352. 353. 354. What we're doing is we are looking in this box right here. And eventually we're going to start seeing right about 62. We're going to start seeing a little blip of light. And when you can first see that light, that's the wavelength that you input into the Google Sheet. 377. So at this point, I can see violet. 82, 383, 384, 385, 386, 387, 388. Turn on closed caption. 395. And so now we're just reading off the nanometers every 5. 400 nanometers. But every beat is the next wavelength. 405 nanometers. 46. 47. 408. 410. That's 415.
420. 425. 430. 435. 440. 445.
Hmm.
450. 455. 460. 465. 470. 475. 480. 485. 490. 495.
Shoot. People putting in numbers.
500. Good. 505. 510. 515. 520. 525. 530. 535. 540. 545. 550.
This was painful to record when she was doing it,
Yeah. 555.
which is why you heard me say, just do every call.
560.
Yep.
565. 570. 575.
When we posted this, I had people, teachers, had people send me messages. They looked through the whole thing to see where the different colors started. Nerdy.
600. 605. 610. 615. 620. 625. 630. 635. 640. 645. 650. 655. 660. 665. 670. 675.
Still see it.
680. 685. 690. 695. 700.
Yeah.
Oh,
What are you doing?
here.
What are you trying to do?
To mute our mic. Sound. Okay. We stopped it a little early. And yeah, sorry about that. It was a little painful. We weren't really sure how this would work virtually. Bill?
Well, one thing I was thinking about, Sarah, when this started, and yes, you're taking data and you're having to listen and do all that. I think this is a great, and I love doing this when I taught middle school, doing labs that were, I'll say, tedious, because kids have to learn that science isn't always this bam demo thing that happens or whatever. Sometimes it's slow, methodical, like it takes a while, but when you get done and you can see the data and how rich it is afterwards, I think it's good for kids to learn that if they don't like that, then science may not be a great place for them. Because think about people that do high-end research and how long they spend on something before they finally get an answer. And maybe they don't even get an answer, And so I think it's good for kids to do things like this sometimes where it's methodical.
Yeah.
So
Absolutely. And I think you have a point. This is it's tedious to sit. It's almost painful for us as presenters to sit and watch this going like, oh man, this is taking so long. I hope everyone's getting something out of this. It was very nice because Bill had flipped over to the sheet. We could see people starting to input data. What I wanted to point out, just looking at this sheet here, before we even talk about the graph, even with people only putting in data that they observe, you don't have to have every cell have a data input or a point in there. We're still going to get ranges for the wavelengths of each color averaged out. This is our class data for how we might define wavelength, the wavelength range of violet and the wavelength range of indigo. Something else I wanted to point out, I don't know if this is the right time to say it or not. We start at a point where we don't see any color displayed in that box. It starts out there, probably nobody observed a color point within that box. But then at a certain point, some people about the 370s, maybe high 370s, or maybe low 380s, we start seeing that violet point, and then we start putting that in. It's important to have that outer boundary or both outer boundaries for violet and red there, because the data isn't there to begin with because our eyes can't detect ultraviolet light. That is technically probably like the far UVC light that we're seeing that we just weren't quite seeing right there. But then once it hits that visible violet light, then we can detect that. And then the same on the red side of the spectrum. At a certain point, and I know that when we did this lab with students, they just felt like once they hit red, they were done. Well, no, you're not really done, because the color of red that we observe does have an outer boundary that eventually it will fade. And that's exactly what we saw on the video, that it fades and then goes into infrared, where we talked about we can't see the infrared light with our own eyes. So the spectrophotometer.
Question. Then how come I could see my red on this?
Well, it's a laser that you're seeing, but it's not.
How come I can see my blue on this? Or
It's just butting up to those violet wavelengths.
it's broader. It's broader than, it's not just the ultraviolet.
Mhm.
It's broader than that, which is why. But these are questions kids ask.
Oh, yeah.
I can see red. Why can I see red? Well, actually, it's the laser that's coming out of there.
Absolutely.
But
Yeah.
but on these and black lights and stuff, you can still see that violet purple
Mhm.
glow. Well, that's because it's broader. It's not so narrow. It's just giving the ultra.
Sure.
And so those are questions kids ask every time.
The spectrophotometer too, I know at the beginning Stephen had said, well, do these instructions work for every spectrophotometer? And the answer is no. But the point is these are easily adjustable. I think we had specified in the procedure to set those initial wavelengths to 325 nanometers, because that's what the Genesis spectrophotometer registers. That's its lowest boundary for wavelength. If the idea is you just want to go as low as your spectrophotometer measures. So if it's 330, if it's 315, whatever that lower boundary is, and then the idea is that you're cycling through all of the wavelengths that that spectrophotometer is able to emit until you get to the end, which probably is outside of the visible light range of red. And it might be like, I think on ours, it was around, was it 680?
It goes over 7.
680. Red does, but this spectrophotometer, again, it gets into a little, I think that's
So I
something
just
else.
meant the spectrophotometer.
Oh, the spectrophotometer does, yeah. You're going to see sources that might define the wavelengths for each color slightly differently. This is just what our observations are. And so I think you can have an interesting discussion about, so what's right? Is our data correct? What might be limiting our data? And so some of that data might be limited definitely from the instrument that we're using. But then I think also, user yeah, exactly. How you interpret it. What if you suffer from color blindness? How might that affect?
What do we know if everyone sees color the same?
Well, exactly. I'm not sure we do perceive color the same. So
Well, it'd be fun to do this with a class and have half and do two of these graphs, two of these setups. Have the girls do one and have the boys do the other.
Oh, that would be very interesting. Yeah.
That would be fun to do.
Mm-hmm.
Because
Start experimenting, see if eyesight's different by different.
yeah, well, and they say girls see more colors than guys do. That's
Do they?
why. Oh, they talk.
You talk to them. You talk to the mystery they. I don't.
I talk to them all the time. Well, you talk about when someone says something's fuchsia or something is whatever, and we're like, what?
So what would that color be? Right. And where do those colors like fuchsia and brown and, these other shades that you can get into, those are not listed in our Roy G bid, like what we have to find here. So then, yeah, those are some other good discussions to get into. This is a waterfall chart that I wanted to talk about right here. I love this chart. I love graphs in general. I taught math. I really do. I love data. I love how this is visualizing this data. It took our team a little while to figure out what's going to be the best way to show this, that's going to make the sense, that's going to give us that defined range for each color. What this graph does is it's graphically showing the continuous nature of white light, that for each, when violet ends, that's when indigo begins. Even if we're not all observing the color indigo, it's those of us that are observing the color indigo that we're able to include that, and that it's factoring it in. We can also refine these boundaries that we're calculating the more data points that we add. So the more observations that are taken, the better that wavelength range gets for the set that we have. But that you're going to see that there's no gap, that as we go along, that it's continuous, that every wavelength from about 3.7, just over 378 until just under 680 is represented within this. And so, yeah, I just think this is it's just a neat type of graph. It's probably a different type of graph that students might not have encountered before. And it's just another way of visualizing that data.
It's pretty cool.
I think so. So we need to go back to, okay, right here. Okay. So again, this is just another link to get back to that page. You have that copy of data that we have all shared. We all have that copy now in our drive, but you can get a clean copy, again, either clicking here or up above, there's that link as well. But again, you want to make a copy for your class, however you want to share that with your students to get them to enter that in. And then, our discussion questions, which we spent a little bit of time talking about, that how do your observed wavelength values for each color compare to the wavelength values displayed on the graph? So we could go by each row and say, okay, well, I observed, orange ending at this wavelength, but the graph is showing that orange is encompassing all of these wavelengths. I'm only inputting one, but we're giving a range of values that orange could be, that we're detecting orange as. Why might your observations of colors at different wavelengths be different from the observations of a classmate?
Because they're wrong.
And why do we show individual colors as a range of different wavelengths instead of one single wavelength? And I'm not sure that there's any one right answer for any of these questions, but I think they're definitely worth discussing as a group. And from this, we have a podcast episode from, again, our Superheroes of Science platform. We have a podcast, Science from the Experts, and we'll talk a little bit more about this in the next lesson that we're going to show. But specifically for this visible light lab, we have an astrophysicist that uses the electromagnetic spectrum to study different planetary bodies. And for these, we have the podcast only. So if your students aren't able to access YouTube, that's not a problem. They can listen to the podcast. We also have videos for many of our podcasts that they're able to watch. They can kind of see the scientists speaking about it. And then we're in the process of building guided listening worksheets for these to kind of help students as they're listening. This is just a nice supplemental activity as kind of a follow-up, an extension of how professionals, STEM professionals really, are using these concepts in their research that they're doing right now. Down below, we see a couple of other resources specific to visible light. One of the very first ones at NASA, it's a science mission director, it's a NASA link. Then we saw another visible light spectrum chart that they might use to compare. Students could maybe use that chart to compare to the class data and see how it differs and why there might be differences in those wavelength ranges. And then down below, we have linked this particular virtual lab to the next gen science standards, both middle school and high school. It's appropriate for both. But then we've also, just in case it would be helpful, included some connections to both cross-cutting concepts and then science and engineering practices, along with examples of how this virtual lab might tie into, each of these. So there's that. I think we might want to pause and just ask, are there any questions now that we've just gone through this that, or comments that anyone might want to put out about the virtual lab that we just went through?
So if you have questions, please type them in the chat. All right, I would even, if you wanted to raise your hand.
Oh, yeah.
I mean, there's not that many of you in here, so we could rate, if you want to raise your hand and unmute yourself and ask a question, we could do that too.
Oh, I love that, Shauna. Yeah. Yeah. Students ask if we all see colors the same. And I think that's a great, you could even design an experiment within your classroom, like what we were just talking about, where the kids could be part of that. Like, how might we test whether we're all seeing those colors the same? And,
I did think Bill's suggestion of doing different variables of whether it's gender or
Glasses, no glasses.
oh,
yeah.
I mean, I'm thinking of all the things that,
One thing, the kids who are really good at art.
oh,
Oh, yeah.
Art kids.
Yeah.
Do they see things differently? They think they're, I mean, I know the things my daughter does with art, I could never do. So I kind of wonder if she's seeing it slightly different than me.
you know, and
Right-handed, left-handed, I don't know.
And the cool thing is, that as a teacher, I mean, it's really cool if you think about, if you have 100+ middle schoolers,
Oh, yeah.
you got a good data set.
Absolutely.
And if you could figure out a way to even subdivide that so you would know who's what, you could take that data and remove it and move it into another and
Oh, yeah.
you see what I mean?
And I think, data visualization and big data, I think these are all terms, we're hearing this a lot here. And I know that, that students more and more have to be comfortable that every student, if they go on to any career really, whether it's college or not, they're going to have to know how to handle data, how to look at data. Like this is just the society that we're moving into. And so I think that there are some really great opportunities, like Bill's saying, and you too, Steve, for figuring out different ways of testing this or different things to do with the data that's being collected, especially in these smaller classroom settings.
I like what Chris said. It fits in with waves and I lost it. when we get into color, it's what we call different colors of social construct.
Oh, yes.
Yep,
That's excellent. Yeah.
sure is. You ready to share the, you ready to go over?
Yeah,
You
yeah.
gonna go over this?
Into remote sensing.
Yeah. When you do this.
Okay. So our last kind of resource that we're going to be sharing gets into remote sensing. So, we started with an introduction to waves. Stephen had that question, we kind of, that page has that question, why do we things
Car
heat up?
warms up,
Yeah,
yeah.
car warms up. Why does this happen? How come it might heat up that quicker for us in the summertime than in the winter, but other parts of the world that might be opposite. And so then we lead into then a measurement lab, mainly because we had access to a spectrophotometer. So those were the wavelengths that we were able to measure because that's what we had access to. But now we're going to scientists use waves in a lot of different ways, obviously. And one way that we think is very interesting is this concept of remote sensing. And especially our overarching theme being, our universe, that we're kind of all summer here, we're making these connections to our universe. And we know that our sun specifically, it's very far away. It's beyond what we can possibly imagine in terms of heat. And in order to study the sun, we can't just look at it. We need ways and special equipment that measures all kinds of different wavelengths from it. Using different wavelengths gives us a variety of information, not only just about our sun, but about our planet, about the Earth, about our surrounding planets, and then also about solar systems beyond and galaxies beyond where we are. And so we have this starting statement here: remote sensing is a way of gathering information about objects or places without physically touching them. We can't just go to Mars. It would be great. We have the Mars rover. We sent it there, and we'll talk about that a little at the end. But right now, it's not possible for us to physically go there, to physically collect data and determine things. So we need other ways. And remote sensing uses waves to help us collect this data. So in this lesson, we are going to have students, first of all, they're going to create a painting of our sun. And then we're going to use some different colored filters. We'll talk about ways that you can do this to view the painting that they're making. This is going to simulate using different wavelengths of energy to collect information about this object. So remote sensing is all about utilizing different wavelengths to collect information so that we can get a better idea about whatever it is that we're wanting to investigate, since we can't go there ourselves and collect that information physically. From doing this, students are going to better understand what remote sensing is and explain how different remote sensing techniques might work. So you want me to go through this?
Yeah.
You want to talk about okay. I'm going to pause for just a minute.
They like running that car.
Yeah, they do. We're clearly in a high traffic area right now.
I guarantee that's a doer.
Yeah.
Yeah. All right. Sorry.
Yeah. So the very first activity in this lesson it's called painting the sun. What we do, and you can kind of see this picture here. Really, picture says 1,000 words. We have this little dish, and we put in some paint and then some dish soap in with it. And then we have a straw, but we want one student probably to be the designated straw user, because we do not want to share germs through this activity. But the idea is that you mix this paint and dish soap together. Do you have to remember the ratio, Stephen?
It's in the procedure.
Oh, is it? Yeah.
It's in. Pretty sure.
Yeah.
Yeah. See.
8 tablespoons of dish soap, and about half of that being the paint in one bowl. And then we use the same in a different bowl. We use a different color. So we used, I think, yellow and red for this. But the idea is that students, they create these soap paint dishes. They mix them, they blow in the bubbles like what we see happening right here. And then they take a sheet of paper and actually it works better if it's like a thicker paper, like cardstock, over the bowl. And they gently press around the rim. You don't have to press in the middle because the paper, you don't want to pop any of the bubbles that are there. The idea is you just want to collect these bubbles on the surface of the cardstock. And then I think we let it dry just a little bit, and then we go back to the other paint bubbles and we relay that same paper on top of it to kind of superimpose that. So that we end up with the two different colors kind of lined up on the same sheet of paper, and then we let it completely dry. So at this point, we're going to stop this. We'll show you an example of what this paper kind of looks like. So you can see where our bowl had created this. We see some different colors that you can kind of see. We had yellow, and I think we had orange.
Red.
Or it was red. Okay, yellow and red is what we had. So this is what we end up with.
Reddish.
Right, yeah, kind of reddish. And then
Yellow, red, and ink orange.
yeah.
The red was just slightly more watered down when we did it.
Oh, that's so we're going to keep the screen share off for just a minute. We're going to show you, we're going to try to use through the camera lens and see. Might have to use the, okay, that's what both, wasn't it?
Yeah, you can see it, but not on there. Oh.
Okay. When we use the yellow filter over it, the yellow paint, we can't detect anymore, but we do see the red coming through there.
It literally blocks someone.
Oh, the yellow is kind of light. Would it work better to hold it over the camera?
No, it literally blocks, the red blocks both. See,
Oh, yeah.
you can barely see it. I have an orange
Okay.
that doesn't block it too much.
And these are just sheets of just cellophane. I think we found these, online. We were able to get them in.
Oh, there we go.
Oh, now we can see that red coming through that.
Yeah, that's nice.
Mhm.
But using the different ones, it kind of reveals different things in the image. Just like using wavelengths in remote sensing, we use different wavelengths to see different things in our remote sensing. And what we used made is that's just PVC pipe with PVC couplings to hold it on. And we just shoved, had to use 2 layers when I did it. Just two layers on there, cram the PVC fitting in there, and then you have a viewer. These we hung up in the
Yeah.
classroom. After the students did them, we let them dry. Then we hung them up because everyone's is different. They're all slightly different. And in this one, you can see the reds, the pinks a little bit better.
Oh, yeah,
You can't really see the pinks in this.
right.
And so they're slightly different. And so then the groups, they can go around and look at the different ones with different lenses.
The PVC is optional.
Well, you look like sunburned a little bit there.
Yeah.
Yeah, you can use paper towel.
Yeah.
You can use paper towel
Tubes or.
tube and just stick a rubber band on it. You'll be fine too. But we had these left over from another project. And it worked great to hold that on there nice and taut. And students weren't dropping these then. They dropped the whole thing and that didn't hurt anything.
So when you do this, this is my curiosity.
Mhm.
So I've noticed you guys have used a lot of red, yellow, orange. But you could use all different other colors.
Yeah.
Like purple, blue, green. PVC cutter.
So-
Yeah.
So literally,
But if
the
you
bubbles,
use
the bubbles,
something, you want to make sure you have those. If color paint, you want to make sure you have those. We're going to show you an image of why that's kind of important here in a minute. But you do want to have those. Now, will this filter out slightly different things and you'll see, yes, you'll see slightly different image. But, what were you saying, Bill?
well, I was thinking this would be a fun thing to do before you. So let's say you do one. I would like as a teacher, I would have one that I already made and have the kids look through before they make theirs.
Mhm.
And then go, all right, so let me ask you, if you use green paint and red paint, what do you think, what filters do you think are going to allow you to see something different? You know what I mean?
Yeah.
So that they're maybe thinking ahead, and whether they do that to have misconceptions
Mhm.
and then have aha moments later, or they actually can justify why they said what they said, or are they just guessing? All those things we do as teachers, right?
I would pass that part on to our teacher.
Well, but I'm just thinking,
It depends on what you're doing.
well, but I mean, the whole idea is, but you're still thinking about remote sensing and the fact that they don't always just throw the kitchen sink at everything. They have some thoughts as to why they're doing whatever they're doing for remote sensing, based off
When you
of
tie it in that way. so-
preconceived notions as to why they think
Yeah.
using this, I will be able to maybe see something
Yeah.
like this. That's what I was going towards.
Yeah,
Not the color thing, but
okay.
Go back. All right, back to our lesson. Again, we're, for this part that we just talked about, we are just focusing on the sun itself. And again, you can see a different picture.
It just says but it can represent any planetary body.
Absolutely.
It just, this one, we're like, okay, the sun,
Mhm.
this works.
Yeah.
But really, if you start looking up infrared images and false color imagery,
Mhm.
any planet that you see in the distance will look, depending on what we're using,
Right.
like this.
And you know that the James Webb Telescope is a great example of this. The data that we get back from this isn't necessarily the beautiful pictures that are then shared out, like, oh, look at this, this Crab Nebula, this, one of the very first, whatever it is, all these pictures that come out they had to look at those and decide the best way of, again, visualizing that data that was collected from that to make meaningful images that say something. So then this all just talks about, again, using those viewers. Like we said, we have the PVC tubes from a different project, which work beautifully, again, with those couplings, but any tube, like a paper towel roll or something like that would work, or even just using the cellophane like we did at first, overlaying it on that picture works just fine. So Stephen, you found this, you want to talk about this here now?
Oh, well, that was an artist that I found online, and I absolutely love this. That he uses it's 3D. It's 3D painting using different colors, and so he basically is painting two images on there. And with him, and he's not the only one that does this, but his is very popular throughout the world. He paints full murals doing these two images. And then if you look at it through red, for this one, you saw the stormtrooper. And for this one, you saw the Jedi. And so, because you haven't seen these, have you?
No.
Did. So
Yeah.
you'll have to watch a movie to find out why he chose those two.
Like, remember, I read the last page first, so you can tell, but maybe other people don't want the spoilers. So.
Everyone else in the world has seen.
I know. Yeah.
hey, it's his father.
Oh. Okay.
No, it's not.
I'm just trying to help. I'm trying to help misconceptions.
No, it's him.
Oh.
He was a stormtrooper. He's a stormtrooper.
Oh, I couldn't see. Oh, now I see who it is.
Oh, okay.
Wrong movie. Oh,
I couldn't tell which.
I can't work with these people.
Hey, we can't quit you.
Yeah.
He wasn't a Jedi. He's not a
He
Jedi.
joins the Rebel Forces. No, he's not a Jedi, but he joins.
You said Jedi. That's why it threw me. Okay, that's not a Jedi.
You're right.
He says he was with the Rebel Forces.
Yes.
Okay, all right.
Yes. Yes. Anakin.
On my screen, I could not see that.
That's
To my.
Okay.
well, you'll have to look through his stuff. He has a website there, and there's other artists to do this. I just thought a lot of his, and since we like Halloween for our house, a lot of his has like skeletons. You can see a person one side, then you look at the other color, and you can see the skeleton,
Nice.
Oh,
which was really cool looking. And I think it's one of those groups I was in that shared that.
Yeah.
I'm like, all right, that's so cool, and that fits in with what we teach. So
Absolutely. Yeah.
we that's awesome. But anyway, using wavelengths in our
colorblind tests. And I know we didn't find any of those and we didn't create any of those, so we didn't share that. But those like blob, you kind of look at them, you're like, oh, what number do you see? You know, I think that's kind of on in that same vein of when we're trying to use these, you know, just different colors or just different ways of putting those together.
Which is, go ahead.
Yeah,
Finish.
yeah. So I know like if you don't have color blindness, you may be able to see those numbers hidden in there, but if you do, you're never going to see that number. And so I'm sure that we can Google some of those and see that as well. We are
And,
going to,
oh, you want to talk about the podcast resources before I do?
yeah, definitely. So
What ones did you put there?
do we refresh it? There we go. Yeah. So this is the same podcast that we had mentioned for the visible wavelengths. It also is applicable to this remote sensing as well. In fact, in this, Demetrios does go through the same picture. I believe it is of the sun. It's the sun, or it's another exoplanet maybe. But under all of the different wavelengths. So it's an image of the sun using X-rays, and an image of the sun using visible light, an image of the sun using microwaves. And it's really neat to see that same image, but then displayed using each of the different wavelengths that they were able to take. We also have identified, we have a whole list that we think might apply to remote sensing, but we only included a couple more that definitely do apply to remote sensing. We had discussed the Mars rover before, the Perseverance rover. We can't go to Mars, but we've sent rovers to Mars. We have a couple of faculty here in Stephen's department who specifically work or have worked with NASA on these rovers.
For NASA.
Or for NASA.
They say Roger worked for, he came here from NASA.
Oh, okay, that's right. Yeah. He specifically had designed both ChemCam and SuperCam, which is how they're identifying rocks that are there on Mars. So it's one of the sensors that's on the rover that we have there. So again, podcast, audio only, YouTube video for that. We also spoke with a NASA scientist who his goal, what his research is, he is specifically looking for alien life in the universe. Evidence of alien life in the universe. So they talks about the Goldilocks planets and alien smog and how we might detect some of these. So again, these efforts are possible through remote sensing.
And yes, he wore a Star Trek shirt for the interview.
Yeah, it was super impressive.
Yeah, and with remote sensing,
Turn off the thing first.
yeah, I'm gonna turn that off. Yeah, that's what I was gonna do. Bill will hand you the light, and you have to start at the top. Can you see it on there? Start going across. Oh, are you too close? Or does that camera not pick it up?
Go come closer.
The camera doesn't pick it up.
You know, I don't know if the camera's picking it up.
Yeah, I can't see it.
You can see clearly, Bill?
I can see it very clear.
Oh, the camera's not picking it up.
Huh.
Wow. All right, so we used the UV marker. We wrote a message on here.
It must, you know what it is? It's an Android.
That is not an Android camera.
Okay.
You think the tube?
What if we turn off the lights? I mean, it's worth a shot.
You can't see it on ours either.
Let me turn off the lights and then just to see.
All right, Bill wants to show up lights.
If that's too bright, it might work better.
Everybody has a different idea how to get to work. It's not picking it up.
I think it's just too. The camera's not going to pick it up.
Yeah.
Wow.
Well,
Huh, all right,
we might have to punt.
all right. I guess that, should we tell them what it said?
Yeah. I think you should tell them what you did.
Okay.
All right, so we took a UV marker.
Yeah. Invisible ink.
And then we used UV light to represent our remote sensing to discover the message. And what message do you think we wrote on here?
Well, our pre-discussion before we started, recording.
We couldn't record that.
No, before we were recording, we were talking about an adult beverage.
Oh, Yeah.
So you think it's adult beverage in there?
No, I don't think so.
We did not put anything about margaritas.
No.
Well, what would you put on here? What message would you put on here for adults? Well, it's not like, it's still, no. It's not like.
Yeah. Oh, gosh.
Um, that
What would it-
sounded terrible.
That did sound,
I
yeah,
was thinking more, that kids might not get it. Well, I think they'd still get it.
that they would. Yeah,
I think
it's
it's okay.
in the, at least,
I don't know. I'm gonna ask my kids when I get home today if they understand what that is.
okay,
Yeah,
I don't think they will.
I've seen no guesses in the chat.
All right,
okay.
go ahead, tell them.
We have to tell them?
Yeah,
Yeah, well, yeah, they're not gonna be able to see. You can't send it to them.
Okay.
all right.
It says drink your Ovaltine. And subscribe to Superheroes Songs.
Drink your Ovaltine.
Reach your Ovaltine.
There we go.
Yeah.
But, and if you've ever done a breakout room, you probably have seen these.
Yeah.
A lot of breakout rooms use these for clues. And so, but what a great way for kids.
We do lockbox activities, which is
Mhm.
why we have these. We do a lot of lockbox, and on our site, we'll show you where to find some of those on our site.
Yeah.
Because they're geared towards middle school level anyway.
Yeah.
We'll show you where to find that. Did you finish that page?
Yeah, let's go back and finish up. I'm pretty sure that was the end of it here.
I think it was.
Yeah. So here we have the resources listed. So yes, I think at this point we are ready to go into where do we find some of these?
All right, we'll show you real fast where this stuff is. If you just type in like Purdue College of Science, something like that, and come to our outreach page, then go to teachers. Is that really the first thing?
Mhm.
Okay, well, this is professional development. You've probably already found this page and the more information. And so this is the stuff from last summer, recorded sessions, the conference. Which one is it? Is it here?
No.
Where am I going?
So we're going to the middle and high school virtual labs and resources.
So we're going.
Under lesson plans.
Yeah, under lesson plans and resources.
I cannot see where it popped up.
There we go.
Oh,
Oh, no, next, the tab next to it. There we go.
woo, here, you take this.
Okay.
Because it, obviously I can't be trusted with it.
Okay, so this brings you to our virtual lab page. So again, it's under,
You put the link in the, just throw
yeah,
the link in there.
I'll just put the link right in here so we can,
That way it's easy for them to find it real quick.
Yeah. all right. Go back to this and so we've shared the link to our virtual lab page with all of you. We will be, after this recording, we will be linking the, well, two of the lessons will be linking, well, they're all three on there, aren't they? Yeah, all three of the lessons are on there. Last week, we had our introduction to radioactivity. We also had our what is half-life that we will be linking on that as well. We have our science demo repository that we'll talk about here in a little bit. Here you will see our wavelengths of visible light lesson that we went all the way through. So that one is listed. We have one classifying matter that was from a couple of years ago. That's a different virtual lab. A really popular one, our groundwater contamination lab. We get a lot of requests for this answer key from a lot of different places. Air pollution, states of matter. Photosynthesis is not complete. We've had some supply chain issues.
Stay out of that one.
Yeah. This is what we started with today, this investigation in Earth systems, where we had the introduction to waves, and then the different links to YouTube shorts and things specific to mechanical waves, and then the shorts specific to the electromagnetic waves. We do have listed, we're going to hope to add to the electromagnetic wave shorts as well, hopefully, but those are listed there. Some of these are a little beyond, I think.
A lot of those are high school. The ecology all around us is a good one though.
Yeah.
That's one that we could do in middle school if we do an ecology unit, if we want to do an ecology unit or something.
We're gonna pause for a second. There.
It's construction, so
Is that what it is?
see.
We
So
will
there's-
add the remote sensing. I think we need to add the remote sensing
Okay.
lesson to this page, so we'll get that added as well. I know on the Earth Systems one that we started, investigation in Earth Systems, we need to add the radiometer lesson. So we're going to make sure that that link works as well, because that's kind of fun to use when you're, again, going back and talking about those waves. But the next thing I'd like to point out would be our science demo repository. And if I click on that, it brings you to this first page, kind of the intro page. But then this link right here is where you can go and search this enormous repository. I don't know, hundreds. I don't know how many videos we have listed. But you can just see if you go in just a keyword search, and I did wave, and you're going to see, and it'll tell you on a lot of them whether it's the full demo. Full demos were shot for teachers.
No.
With some background information.
A full demo you can show to students still.
Oh,
There's some that say teacher, it'll say teacher.
teacher version or something.
Yeah.
Okay.
Full demo just has the entire thing. It's one of Austin's.
Oh,
It has the
okay, that's
entire
right.
thing. If there's some that have like background stuff. Oh, because it's under wave. We don't have any of those under wave. The teacher only one will say teacher edition.
Oh, okay.
And that's telling you the background things behind it. You
Mhm.
need to know maybe some safety or how to set up the demo and stuff like that. And so that's where those are.
Okay.
The others, the full demo, yes, he explains it as he goes.
It's just not in this short.
The others just a short, which we just take the action piece. And those are really good for phenomenal.
Mhm.
And so with those, some of those you can shut off sound, others you can't shut off sound. But a lot of those be good for phenomenal.
Mhm. I agree.
But yeah, the teacher edition ones will say teacher edition on them. So there's a bunch of demos. So if you want to show a demo, some of them you can't do in your classroom. And then some of them you just want to see someone else do and explain before you do it.
Right.
And so
Yeah.
that's what this thing's all about. 141.
Oh, okay. And it was over 100.
There's
Yeah.
some of the students that finished editing some. I saw they finished some things. I need to add more.
The nice thing, we keep adding to the demo list as well. So it's not like we have all that we're ever going to have. As we have time, we continue working with people throughout the College of Science and beyond to continue adding to that demo repository.
But anything else, or we just want to go to questions?
Go to questions. I don't know, do we want to show the kids STEM degree?
Okay, yeah, where is it?
That is,
It's down.
yeah, down. Oh, lockbox lessons and resources too.
I guess we
Talked about
told them,
that, Yeah.
Lied. The lockbox ones that we put together that we've done it, I don't know, we've done with Hasty and I think in STA even 1 year,
Mhm.
but some of the different ones we put together, Elements, Earth and Sky. It's been a couple of years since we've done that. Is that the weather one we did? No, weather and climate. There's the weather one. Oh, that's the element one. We did for the middle school thing.
Okay.
It talks about the elements
Mhm.
and something, I don't remember. Periodic table one.
Mhm.
That's you did some good stuff.
Yeah.
You did some good stuff. Gateway to the Stars, that's when we collaborated with the math continuing lecture. Great mission or step-by-step thing they had to do.
Now, I will say, I got a notice, I think later this year, Jamboard is shutting down. So for this one,
Oh,
we're gonna have to figure out what to do with our Jamboards, but that's something,
add that to the list.
yeah. So.
But all right, and what else? You said STEM degree.
STEM degree. If you've not seen our STEM degree materials, we are also working with faculty to create new degrees, STEM degrees in certain content areas. These are kind of made with the idea of being an enrichment piece that can supplement what you're already learning. It's just fun information, fun science videos. The idea is that within each degree, we have 10 videos that the student watches a video, answers a couple of questions about the video that we provide a link to. And if they answer the questions correctly, they get a code. If they collect all 10 codes within that degree, they can submit those codes and it automatically emails them a PDF of a Purdue STEM degree with their name and their date and their teacher on it, that they input all of that information and then it generates that.
I know we met with a faculty and her grad student this week on one on geomorphology. And
Yes.
so I think he's starting with hills and landslides and stuff like that. But so there'll be one that it covers a lot of that.
Mhm.
And so I say that because that's kind of permanent. That's the middle school levels.
Absolutely.
We teach a lot of those concepts and I think they'll be going over. And then the geochronology they'll be doing next, that particular group will be doing next. Then we have a couple of other groups that are working on some, I don't even remember, I think. What's his name's group, are they working on the earthquakes and faults one?
I think, oh, no, right now, I think they're just doing a different video.
Okay, I couldn't remember what they were doing.
Yeah.
But I know that's in their grant. But,
So the point is, we are also expanding these degrees as well. We do have, right now, we have one middle school degree. We also have one calculus degree, but each of these includes 10 videos, again, that are just nice enrichment videos to share with students. And then they can get a really nice artifact from that.
superhero science is what all our stuff's on, any social media you're on. But we do a lousy job posting, but we're gonna try to do better. I think I say that every year. We're gonna try to do better about posting more of our resources when we create them. And of course, our YouTube channel, we pump out stuff on there quite regularly. Cause it's stuff that we do and teachers do, or well, actually sometimes, yes, teachers do for us. And lab groups and Purdue classes, some professors have their students making stuff. Bill, we don't need to be recording name. You want to kill that?
That's what I was waiting on. Okay.